Welcome back. This afternoon's session is supported by renewable energy aggregators. We will hear first from the customer side of a flow battery business with Adam Rouselle of REA and from Kenneth Davies of Birch Infrastructure. Mikhail Nikomarov of Bushveld Minerals will join us. They're a supplier of vanadium, one of the key components of many flow batteries. After they've spoken, we will broaden the discussion by inviting two flow battery manufacturers, Rick Winter of UET and Henrik Buschmann of Schmid, to give their views on how flow battery manufacturing can expand to meet the challenges of the next few years. Let me introduce Adam and Kenneth. Adam Rouselle is the President and CEO of Renewable Energy Aggregators, REA. Adam is an expert in electricity transmission and a serial inventor. He has developed pump storage projects and negotiated successfully with the FERC, that's the American Federal Energy Regulatory Commission. Kenneth Davies is co-founder and Chief Strategy Officer of Birch Infrastructure, specializing in owning and operating the energy and water infrastructure for hyperscale data centers. He is an expert in energy management, having worked for a wide range of companies, including Constellation Energy, Charles River Associates, Cambridge Energy Research Associates, the National Renewable Energy Laboratory, and the Rocky Mountain Institute. He was the first energy expert on Google's team. He created Google Energy and was the clean tech advisor to Google Ventures. He was also Director of Innovation for Energy Strategy and Research at Microsoft, where he was responsible for overseeing the company's wholesale renewable strategy. Adam and Kenneth will talk about the energy requirements for the fourth industrial revolution and its implications for the flow battery industry. So Adam and Kenneth, welcome to the IFBF. Please turn on your microphones, and I think Kenneth, you may need to start.
Yes, good afternoon, everyone. Good morning to folks, here in the United States and elsewhere around the world. I think Adam will be joining us shortly, but I'm happy to dive in and share my presentation on the applications of flow batteries in hyperscale data centers. I want to go to the next slide. So if hyperscale data centers can be defined as data centers which are generally 10 megawatts and above. There's really been an explosion of these data centers over the past decade or so. When I began in the industry in 2010 at Google, a large data center was 10 to 20 megawatts. The data creation since then has absolutely exploded. Last year or 2 years ago, there were 33 zettabytes of data created. To give you an idea of how much a zettabyte is, if you were to go on Amazon today and order 33 zettabytes of hard drives, the cheapest ones you could find on Amazon.com, it would cost you approximately $100 billion. Of course, the data centers, when they purchase hard drives for hyperscale data centers, don't pay retail price, but it gives you an idea of the scale of the data. Data is exploding and energy consumption is increasing exponentially as well. What you see on the chart in front of you is a logarithmic chart, graphing the growth of those two. Energy consumption is trailing data consumption because of the efficiency. But still, you look at the energy spend, and it is getting very large very quickly. To give you an idea, when I was at Microsoft prior to co-founding Birch Infrastructure, the approximate energy spend there was over $1 billion a year and growing at about 25 to 30% per year. And Microsoft, Google, Amazon, digital, very quickly you can justify that $20 million plus. Next slide. So 20 billion growing to 100 billion in the next couple of years seems like a lot of money, but it's actually relatively small compared to the total cost of owning and operating data centers. When these large hyperscale providers think about data centers, they think about servers. Microsoft, Google, etc. They have infrastructure teams of hundreds or thousands of people. But really what these teams are not energy experts. There are a few, but they are server procurement organizations. Over the life of a data center, about 2/3 comes from the cost of the servers, and they are refreshed over about every 4 to 5 years over that period, hence the very large costs. To give you some ballpark numbers, a 100 megawatt data center, to build it before you put the servers in, the cost is approximately $600 million or $6 million a megawatt, 1/2 of which is energy infrastructure costs. But because of the size of the servers, the energy cost is generally ignored. And the data center providers do not believe this is something that can be optimized. This is for the job of utilities, is the general view. Next slide. So for us, this is where Birch Infrastructure comes in. We help data centers optimize their energy costs, having come from the data center sides ourselves. Google and Microsoft. We're on the outside and helping the data centers apply their leverage against the utilities. The name of our company comes from a quote from FDR when he laid out the vision for the Rural Electrification Administration here in the United States. We are the Birch rod that allows the customers to negotiate a better deal for their energy. Next slide, please. So here at Birch, we work on both the generation and the load side of the equations. This is an example of our first project, which is we already have a signed offtake for this. This is going through financing as we speak. This is a very large project. It is sited immediately next to the Palo Verde nuclear station just west of Phoenix, Arizona. As you can see from the numbers there, the first phase is 250 megawatts of solar plus a 600 megawatt hour battery. If that was installed today, that would be the largest battery in the world, absent pump storage. Phase 2, which we expect to come on by 2023, the size of that battery would be about 1.5 gigawatt hours. So we have the fortunate position of being in the market right now, looking to procure these batteries. These are not cheap. The first phase alone is approximately $130 million just for the battery. So as we go through the next slides, I'll be talking about the applications we see for data centers, some of the costs we're seeing. But I wanted to highlight this project because we're right in the middle of this. This will be for data centers, really kind of first of a kind. And we're going to share some of the insight and some of our views on what is needed for flow batteries to reach this kind of scale and address this sort of customer need. Next slide, please. So when we think about the data center use cases, there's really a whole suite of them. And I've arranged them here from the duration required, from short to long. Obviously, flow batteries are going to be better at tackling the long duration, but I'll go through each of these just to help you understand, how data centers work and how we think about it. So the first, that's a UPS or uninterruptible power supply. That would be sited at the load. And this is needed to carry the load of the data center in the event of a power outage and give enough time for generally its diesel backup generators to come online. Today, these are lead acid There are a few providers who are starting to test out lithium ion. Lithium ion are higher cost, but they have they last longer than the lead acid. So it's about break even right now for UPS between lead acid and lithium ion, but obviously very short duration. The next application that we think about, and we're working on this in some of the eastern markets in the United States, such as PJM, is load shifting. And the required duration is, I have 3 to 4 hours here, but you could probably get away with 2 hours. And really the need here is in many markets, costs, capacity, transmission, and sometimes renewable costs recovered by the system operators are applied on a coincident peak, one coincident peak, 5 coincident peak per year, depending on the markets. By applying load shifting, if you can knock out your load, take it down to 0 during that time, in some cases you will have knocked out 40% of your bill. And many of these data centers, their bills are pushing $50 million per facility per year and rising rapidly. So knocking 40% out of your bill is a very material number. We are currently in Virginia, looking at a 300 megawatt, would be between a 1 gigawatt hour battery approximately, specifically for one data center to manage load shifting. The next product is kind of shifting to the generation side. Again, we look at both the load, the data center itself, and the renewables. Is called TB4. This is an emerging traded product, especially in the Western United States. And it's a financial product that is, the value of which is calculated by averaging the highest 4 energy price hours during the day and subtracting the lowest 4 energy hours during the day. This is traded by the likes of Morgan Stanley and Shell in California today. You can see that the market is starting, in this case, to coalesce around this 4-hour product. Why 4 hours? Is it really the best? In our opinion, no, but like VHS and Betamax, sometimes the market just starts coalescing around the first product to market, not necessarily the best product. The next value that we look at, and this is again on the generation side, is that of capacity value. And this is the number of hours of capacity you need to build for your renewable generation in order to get capacity credits. And in the United States, that currently ranges from 4 hours in California to 10 hours in PJM. Ironically, the needs of the system are almost reversed. In California and the West, because of the integration of solar, you probably are needing about a 6 to 8 hour battery there today to really provide capacity, and that's going to lengthen with the increase of solar, which we'll talk about in a couple of slides here. But the rules and the regulations are 4 hours, and that is primarily because in California there's a very pro-renewable and a very pro-battery lobby. So what they have done is they have set the bar to get capacity credits for renewables plus battery at 4 hours, which if when using lithium ion is much cheaper to obtain. Conversely, in the Eastern markets, specifically PJM, in order to qualify for capacity value, you need to have a 10-hour battery. Now, the market in PJM is deep enough and flexible enough that you really don't need 10 hours of storage. We did a back test of dispatch of storage in PJM market over the past 4 years, and an optimal dispatch, even with a quite high efficiency, is going to be in the 4 to 4.5 hour range. We believe that will increase as you have more renewable penetration come into the market. But as of today, the required number of hours for capacity value in PJM is 10 hours. And this was really set because of the leverage that a lot of the thermal generators have in setting the market structure. They don't want batteries coming in and challenging them for their capacity value, hence the very high bar in PJM. The next one I want to jump to is, and we'll go into the next two in depth, is shape risk management, or what I think about as financial firming. Renewables are intermittent, as we all know. So what is the number of hours you need to really manage your diurnal energy profile and the risk of your cost of fill power? What happens when the wind doesn't blow and the sun doesn't shine? How much does it cost you financially to go and fill that resource? The next is what we call 24/7 renewable supply. This is the emerging need in the market, or desire in the market, especially by data centers, to say that they are 100% green all the time. This starts becoming much, much more expensive. Today, Google's promulgating this standard, and I don't think they really understand how much they're going to have to spend to get it. We will talk about that in a little bit. Those were both generation. Switching back to the load, I mentioned before that data centers have backup generators. They have backup generators, which are today diesel, for the purposes of carrying the load in the event of a long duration grid failure. Today, they generally keep 72 to 96 hours of diesel on site. Not the greenest application in the world. And when we're talking about very large data centers, the large ones of which are 300 to 500 megawatts, show me a jurisdiction that will permit enough tanks for enough diesel to carry 300 to 500 megawatts for 3 to 4 days. Especially in Europe, those sites do not actually exist. So there is an emerging need for a replacement for diesel and even natural gas. And I will give an example quickly of when I was at Microsoft and we were siting our new data center in the Nordics. Ended up putting it in Sweden. And first Microsoft said, well, can we put diesel here? We want 300 megawatts of diesel. We can all guess what the answer there was. No. So I said, well, what about natural gas? Can we hook up to the natural gas pipeline? And the analysis showed that if you were to, in northern Sweden, try to, fire up 300 megawatts of natural gas recips, essentially instantaneously, you would feel the pressure drop on the pipeline system in southern Germany. At this scale, you cannot have, natural gas generators ramp up that quickly. It just doesn't work, at that scale. So there is an emerging need for backup generator replacements, and again, 72 to 96 hours is the general standard one should be thinking about, depending on what's called the tier rating in data centers. The next will be a renewable microgrid, and you can think about this as an island, or maybe a government application, that cannot go down no matter what. And depending on the intermittency, this is more the seasonal intermittency of renewables. You're going to be looking at a 1 to 2 month duration. In most cases, you're not going to need this, but if you look back over 40 years, what was the coldest and snowiest winter in, let's say, the Northeast United States? How much sun are you going to get during that time? You have to have enough backup to ride through that. So now we're getting to very, very long durations, from my point of view, arguably longer than, is feasible for flow batteries. You're probably talking geologic storage at that point. And the last is an interesting, relatively novel one I'll touch on quickly, which is power distribution and cooling. And this would be a continuous loop of flow for the purposes of data center. So now, why don't we jump to the next slide, and I'll talk about a couple of these specifically. So the first one's the power distribution cooling. Next slide. So I don't know if anyone here was aware of this, but this was a patent that was issued by Microsoft. I wasn't there when they wrote it, but a lot of my colleagues are listed on that, those names there. I'll call your attention to the third bold name, Mr. William Gates. This came out of Microsoft Research. And the concept here is, how do you power a data center and distribute the power internally to a data center using a flow battery loop? What you can see in figure 1 there is you have the grid. It would be connected to, step down to a substation, and then you'd have a continuous flow of your fluid. You see the tanks there. It would be pumped into the data center, and that is the method by which you deliver the power to the servers. You would charge the fluid at the substation, you pump it in, and now you're distributing the electricity, not via step down transformers, AC, DC. You're distributing it via pipes. And it would actually run on to the server, or most likely the rack. Each rack would have its own stack that would use the flow fluid to create the energy. And then where it gets very interesting is that fluid would then be used as a heat transfer fluid to remove the thermal heat. So you're bringing electrical heat into the data center, and then you're removing heat from it. Microsoft has not announced anything on this, but I know it's one of them that they're looking at and certainly have the patent. Not the focus of my presentation today, but I thought it was a pretty cool application. So go to next slide. What I really want to talk about here is that some of the applications around shape risk management and how do we get to 24/7 renewable supply. Not talking about what happens, for an island or a government, but when Google and Microsoft said, "I want 100% renewable," what does that mean? Next slide. So over the past really 10 years or so, the renewable market in the United States and increasingly Europe has really been driven by corporate purchasers. This is a tally of the renewable deals enlisted by gigawatts, over the past 5 years. And to make it easy, I went in and I put green bars in, which are the data center deals. So you can see in 2019 in the US alone, there was approximately 5 gigawatts of new PPAs signed by data center providers. I think you're going to see that trend continue. To put it in perspective, folks like Microsoft and Amazon, in order to meet their load growth times their increasing renewable targets, they're moving from 50 and 60% to 100%. Each of those are going to have to procure somewhere on the order of 1.5 gigawatts of new renewable PPAs every year for the foreseeable future. So those two plus Google alone, I would estimate you're at least 4 to 5 gigawatts between 3 buyers, making them by far the largest buyers of renewables in the world. Next slide. The challenge here is when you're buying intermittent power to hedge your baseload consumptions, you're creating an unwanted risk. And that risk is what happens to your cost of power when the wind stops blowing or the sun stops shining, in the evenings, or the sun goes down. The example of this is what happens in West Texas. Every time the wind blows, the power price is very low. You don't need the hedge. Every time the wind stops blowing, the power price spikes. That's when you need the hedge, but it doesn't show up. So when the shape value, if you will, is the value of renewable energy in the market minus your cost of baseload power. And ideally, you want a positive shape value where renewables are worth more than your average power. But what's happening in the markets is as you add more and more renewables into the mix without the appropriate amount of storage, then they are worth much, much less. And this variability is right now being borne by the data center providers. When you have, folks like Google have 4 to 5 gigawatts of renewable PPAs on their books. They are buying unit contingent power as a hedge to baseload. They are massively, massively exposed to this risk to the tunes of hundreds of millions, if not billions of dollars. But nobody talks about it because, in the data center space, everyone wants to be greener than the other. It's a race to who can do most. And to talk about this risk is almost to admit that there's something wrong with renewables. There's nothing wrong with renewables. We're just missing a solution for that intermittency. Next slide. This is a map showing that shape cost for a synthetic, solar project. So this is a solar project applied to, you can see all the little different colors. There's about 2,000 to 3,000 different solar areas in the United States. But then you see very sharp lines along state boundaries, and other places. Those are the different system operators in the United States. So what you can see in Southern California and Arizona, which is the prices off of the California Independent System Operator, there's been a dramatic solar overbuild. So if you look at the scale, what this is saying is the average value of my solar is about $10 a megawatt hour less than the average value of my baseload power. Now, conversely, if you were to go to Texas, and you can very clearly see just from the colors, the extent, the boundaries of the ERCOT grid, which is a standalone grid here in the United States, solar is worth a lot. Why? Because Texas was one of the first to overbuild wind. So you have too much wind, but not enough solar. So there's a premium being placed by the market on solar. So now you're seeing a whole bunch of solar build out. I would suggest that in 5 to 7 years, this graph will have red in Texas as well. But for right now, the value of solar is very high in that market. Next slide. Now this is the exact same graph showed, for wind. This is simulating, the past 12 years of a wind project in every little one of those graphs, those areas on the chart. And you can see in West Texas, this is the wind overbuild. Whenever the wind blows, power prices are low. Whenever the wind stops blowing, power prices spike, sometimes up to $9,000. So this is what some people refer to as the West Texas wind ghetto. Next slide, please. So we have a very long tail here on this shape risk, and this risk today is borne by the buyers of unit contingent renewable energy. And there's really two types of buyers. There's utilities and there's corporates. Utilities have ways to handle this risk. They have thermal assets, but they also have ratepayers. The nice thing about being a utility is you never actually take risk, you just distribute it to your ratepayers. Corporates don't have that luxury. So they've been taking this risk somewhat unknowingly over the past 10 years to the tunes of gigawatts and gigawatts. So they are holding this fat tail of risk without a way to manage it. When at Microsoft, I was able to, develop some new reinsurance products backed by, the reinsurance industry to manage the weather risk, and that can take the center of the distribution. What happens on an average day? What's the variability of the wind and price? But that long tail is a very, very expensive tail for a financial intermediary to take. So there is a dramatic need in the market for a physical asset to come in and start cutting off my tail risk. What happens when the wind stops in ERCOT and prices go to 9,000? If you had a battery that can last, during that, one day, that 6 to 8 hours, during prices hit 9,000, that is a very, very valuable battery. So this is one of the markets that I would suggest that flow batteries are optimized for. Next slide, please. This is how Google thinks about their 24/7 renewable energy. Google has already achieved 100% when measured on an annual basis, but now they're diving in and saying, well, let's look at it hour by hour. And what you can see there is a kind of a very illustrative and helpful graph looking at, on the x-axis, 365 days, on the y-axis, 24 hours. So there's 88760 little pixels there, just graphed by the percentage of renewable energy. And you can see most of what they had here. I think this was their South Carolina data center. Was mostly solar, and then they had some hydro as well, provided by the utility, and that's what you see kind of happening overnight there. But if they want to go from that to 24/7, where every single one of those pixels is matched hour by hour with renewable energy, they're going to need a very, very large battery, or a lot of very large batteries. Next slide. So what are the type of batteries that are available in the market today to solve this? And I'll group them into kind of three here. And here's a summary of costs, from both Lazard and a very good MIT paper published last fall from Ziegler. And it breaks, the Ziegler paper breaks down technologies into what they call technology 1, which they cited vanadium flow and pumped hydro. Now, what's the difference between that and lithium ion? I think, as we all know and appreciate, flow batteries and pump storage, you can scale your kilowatts and your kilowatt hours independently. When you have a lithium ion, that's a much more fixed ratio. So whereas you may pay a lower price for your upfront kW when you want to scale to additional hours and start moving down that table I showed you, from the UPS to the TB4, to the longer duration, this is where the vanadium flow, all flow batteries and the pump storage really start, gaining an advantage. And we'll look at some of the results from Ziegler here in a second. Next slide. But first, I want to, caution people about looking at these sort of papers and setting this as their target for costs. Lithium ion, as I think we all know, has quite a bit of a head start, and they're already rapidly coming down the cost curve. As I mentioned before, we're in the process of procuring a 600 megawatt hour battery. What you see there is the cost that we're seeing in the market today. Those are real, actual, bankable quotes. We have multiple quotes in that price range. So, unfortunately, the target we're chasing here is getting better. Competitors getting stronger, but I do think that the need is absolutely there. And hopefully, you guys can tell me that the flow batteries are much cheaper than as presented here by Lazard and Ziegler. Next slide, please. So I encourage you guys to look at the Ziegler paper, but I've just pulled out some of the highlights here that relevant to the way we think about renewables. And this first one here is the kilowatts of storage to the kilowatts of output. So if I have a 1 megawatt data center and you look at the x-axis and I want to power it 95 to 100% of the time with renewable energy. This is the standard being set by Google, and the market is starting to coalesce around it. So that means for every megawatt of data center, depending on where I am I in Arizona, Iowa, Massachusetts, Texas, the difference between those are the cost and the availability of sun versus or solar versus wind. Massachusetts, you don't have a lot of either. Texas, you have a lot of both. Iowa, you have a lot of wind, but not a lot of solar. And Arizona, you have a lot of solar, but not a lot of wind. So it's kind of the combination here. But what you see is when you're trying to create baseload power, which is what data centers consume, and you want to be able to raise your hand and say, we are, renewable in the hour, 100% renewable, maybe 95 to 100% of the hours per year. For every megawatt of data center, I'm going to need 2 megawatts of storage. That is a lot. To put it in perspective, here in the United States alone, there's expected to be 40 gigawatts of new data centers installed in the next 10 years. So if this was applied, I'm not saying it will be, it means we're going to need 40 to 80 gigawatts of new storage in the US market. It's probably a little bit of an overestimate, but it gives you the size of the scale just to serve data centers. I'm going to pause here. Why would you need 2 megawatts of batteries to serve a 1 megawatt hour load or a 1 megawatt of load? And the answer is because you may only be discharging at 1 megawatt rate. You may need to be charging at a greater than 1 megawatt hour per hour rate. If you have solar with a 1/3% capacity factor, you want to be 100% renewable, you're going to need at least 3 megawatts of solar for every megawatt of data center. And you're going to need to be able to have the ability to soak that up in the high, sunny hours. Next slide. Similar chart here, but looking at size. And this is where the flow batteries really start to excel. What is this optimal, or is the number of hours we need to meet a 90, 95, 100% in our renewable standard, for baseload power in these different markets? And you're looking, it's a little hard to read the graph there, but you're in the 20 to 40 hour range. This is where I think, to meet the demands of the data centers, and be able to say that we're not being 100% renewable just on a yearly basis, but on an hourly basis, lithium ion and short duration batteries just do not cut it. Next slide. And here's the cost comparison. So this metric is levelized cost of shaped energy, which is a new metric. Everyone's got a levelized cost of something these days. But what this says is it looks at the different shapes that a user may need. On the bottom there, it's a little hard to read, but again, I encourage you to look up the Ziegler paper. You have base load, straight across. Intermediate, it's kind of a peak. By peaker, that would be the morning and the evening. Maybe that's complementary to your solar, or just a regular peaker kind of in the middle of the day. So what it said is if you want to, be able to produce these load shapes with a combination of wind and solar in the 4 markets listed, using either technology 1, which again, defined by Ziegler, is a pump storage or a flow battery, where you can scale the kilowatts and kilowatt hours separately, or technology 2, which is lithium ion or others, where you have a fixed ratio. As you start to try to create these shapes and start to use this, as a way to really power your grid, rather than just, clip a few hours here and there and still have thermal assets on the grid, you have to go to long duration storage. So whereas I know it's hard to read this chart on the screen, I can just, the Cliff Notes version is the short bar, the cheaper one, is always pump storage and flow batteries. The high bar, the expensive one, that is always technology 2, the lithium ion. Now, as I said before, the lithium ion costs are certainly coming down. So shave off, 25, 30, maybe even 40% off those bars, and it starts to become close. But once flow batteries start coming down the cost curve, I think I would expect the ratios here to look similar. In the long run, I think the long duration storage is absolutely the way to go. So that's the challenge I issued to everyone here. Next slide. My conclusion, looking at this and where we sit in the market, the flow batteries already beat lithium ion. I'll say flow batteries and pump storage for many data center applications. Might be market dependent. Might be are you at load or are you on the generator side, but there's a demand here. There's a massive, massive demand. So what we need and what I'm asking for from the community is we need scale production backed by an investment grade warranty. I'm going to spend a couple seconds on that last part, which is investment grade warranty. Why investment grade? Because when we go to project finance, $100, $200 million worth of batteries, if there's any sort of technology risk which doesn't come with a very, very strong warranty, we can't raise the money for it. It can be the best technology in the world, but if I can't buy it at scale with a warranty that I can convince my debt providers of, I have to go with the inferior technology, which as an engineer drives me bonkers. But we're trying to meet the market demand, and this is really what we need. I think the flow batteries are there. We just need to start pressing the gas on the scale and find an investment grade backer to kind of pick up some of these smaller technologies. Put a sticker on it and give the financiers the certainty that they need to finance. So the next slide, and that's the end of my presentation. I'll kind of give it back to Anthony and for the rest of the session. Thank you very much.
Kenneth, thank you very much. That was very illuminating. Fascinating, great bunch of figures there, and I'm sure we'll all be diving off to have a look at the Ziegler paper and pick stuff up later. Adam, I don't know if you want to come in for a few moments before we go on to hear from someone else in the industry and we form the panel. Okay, Adam, I take that, but you're coming a bit later then. So we have a challenge there that rather than talking about 7 gigawatts of new storage, we're really looking at perhaps 80 gigawatts. So we now need to hear how the flow battery industry can respond. Many flow batteries are based on vanadium. So let's hear from Bushveld Minerals. We'll refer to Mikhail Nikomarov. Mikhail co-founded Bushveld Energy to provide large-scale energy storage solutions across the African continent. Mikhail is very familiar with the finance and energy sectors, having worked in the American financial sector and for McKinsey & Co. Mikhail is the chairman of the South African Energy Storage Association and also chairs the Energy Storage Committee for Vanitec, the global organisation of vanadium producers. Mikhail, welcome to the IFBF. Please turn on your microphone and over to you.
Thank you very much, Anthony. Thank you for that introduction, and hopefully everybody can hear me. So let's get to the next page. So with that introduction, I actually don't need to go about me. I think just the one thing I would highlight here is the different hats that I wear. So one is definitely as part of the Bushveld Minerals Group on the supply chain for full batteries, coming all the way from mining and processing, but also the hats that I wear from more of an industry association point of view, and also from a battery deployment point of view. So all of that, just keep that in mind as I walk through some of the thinking that we've done as a company in terms of what is needed for the supply chain and what is our participation in the supply chain. Next slide, please. So I think when we think about what is a battery, and this is looking at the left-hand side of the chart, there's actually a number of components. So there's, if you think about it like a lithium battery or an alkaline battery, there's cells, there's thermal management. You know, these can be put into racks or trays, thermal management, etc. But then there's other components, and that'll be kind of your DC block, right? And in a flow battery, that'll be your cells and your electrolyte. And then there's the other parts of the components, which are the power electronics, transformer, inverter, connection to the grid, maybe some sort of site controller, fire protection, any other kind of bunds that are needed, civils work. So sometimes when you talk about a system, we need to differentiate between what is the DC battery and what is the AC battery. And really the differentiators between the technologies are very much on the DC side. A lot of the components that are more AC, well, there may be requirements for one technology over another. There's a lot of commonality there, as long as the integration has kind of been worked through the different companies. So what I'm going to focus is more on the DC side, talking about the flow battery. So on the right-hand side, you can see that the kind of the major components, and this is a breakdown from on the VRFB. And again, it depends on kind of what price point you use, and here they're talking about dollars per kilowatt hour. But what you can see is kind of the three big parts, which is the balance of plant, your pumps, your hardware, your casing, your piping, things like that. Your stacks or your cell stack, which includes your membranes and kind of the assembly of those aspects, and certainly your electrolyte, which can consist of water, either in case of VRFBs, either sulfuric acid or hydrochloric acid, obviously vanadium, and maybe some other chemical stabilizers. So let's deep dive into those two, as they are kind of the two most important cost components of a VRFB. And if you're thinking about the supply chain, you've got to start with those two. Next slide, please. So on the cell stack, what can you do as we're talking about, if the objective is to really reduce the cost and thus also drive adoption? So one is you can reduce the cost of the subcomponents, right? So you can do that through R&D, getting cheaper materials, maybe simplifying the design itself, possibly buying in bulk. All of those things reduce costs significantly, sometimes maybe up to 75%. You could manufacture faster, right? A lot of membranes are now assembled by hand. There's opportunities to do this through full automation, partial automation, and so forth. And then there's other levers, reducing transaction costs, shipping, things like that. And by the way, economies of scale play a major impact in all of these. Maybe not the R&D piece, but definitely anytime you procure in bulk, it gets cheaper. You know, you're not going to set up an automation facility if you're just doing 10 things at a time. And so that's very important to keep in mind. And actually the battery itself is in a way kind of gets a benefit from assembly in scale as well. And you may not need the scale of, let's say, a lithium ion battery where you need to, you know, produce millions of tiny little cells. But I always equate a flow battery to a car where you are sourcing different components and you're assembling it. So that kind of scale is definitely helpful. So let's talk about the electrolyte, right? What can you do there? Well, you can reduce, maybe you can increase the energy density. So you've got actually more energy per amount of liquid, which also then feeds into reducing your shipping costs, your design costs, things like that. Maybe even your kind of running costs. You can reduce the cost of the electrolyte. You know, you can reduce the cost of converting the reagents into the actual electrolyte. You could, you know, chip into some of the margins, and anytime there's a new industry, margins are higher. You could even create a new process to manufacture. You could reduce the cost of some of the supplies. You know, and you can do that in different ways. One is you could reduce the quality of what's needed as a feedstock, and certainly in vanadium, there's a very high quality that is required because the tolerance for impurities is fairly low. And if that tolerance can increase, then there's some savings that can be there. You could also try to reduce the cost of the material itself, which is very hard if it's a commodity. You know, we've seen that with lithium when cobalt is part of procurement, and then companies start to substitute. Right. Same thing with vanadium. As a vanadium miner, I definitely want to avoid the substitution of vanadium with a cheaper material. But that is also an option, either to substitute in full or in part. And some folks have looked at vanadium chemistries that might include bromine, and thus to try to reduce, you know, part of the vanadium. But there's other things that one can do, and you know, you can think about solutions that are a bit more creative as well. Even if you're not necessarily buying the vanadium, can you still use it? You know, are there funding solutions that might be unique to a technology? And certainly that's something that is not necessarily driven by economies of scale, but definitely a source of innovation. And obviously there's other options as well in terms of, again, supply costs and shipping and things like that. But the innovation on the financing part, I think, is quite interesting, and that's a motivator for companies such as us. Who are trying to maybe reduce the contribution of vanadium without actually removing the vanadium from the flow battery in full or even in part. And so next slide, please. And this is really my last page, just to kind of to share how we have thought about it as a company and what can be done. And so let's kind of look through these kind of five steps, really four, and then a fifth one. So one is, you know, we need to make sure there's enough vanadium. There's enough of this material that is needed, you know, as the sector grows. And one of the things we definitely know is there's enough vanadium in the ground. You know, so the question is, and what grades does it have? You know, are there enough companies who are doing exploration and finding this material and securing the license to actually take it out of the ground? So we know there's enough material. Is there enough companies that actually have the resources? You know, the next step is, do we actually have the infrastructure to take this stuff out of the ground and really convert it into a commodity, right? Into some sort of vanadium oxide that can then be converted into electrolyte. Likewise, we also need those facilities that can convert that oxide into electrolyte. And if I need gigawatt hours of batteries, I need gigawatt hours of electrolyte production capacity, which means I need gigawatt hours of vanadium extraction. You know, and 1 gigawatt hour is about 5,500 kilograms of vanadium, or 10,000 tons. So it's a lot of vanadium that is needed to supply that. And, you know, we had discussions where there's one battery, you know, that's being built in China. You know, it in itself is about 5% of the world's vanadium just in one system. If it's procured over 1 year, that can actually really impact the supply and demand balance fairly quickly, especially if you've now got not only China deploying this, but also Japan and also the US and also the UK. So those are factors that are very, very important. And there's got to be a match between how demand and supply increase. So then the other part is around the innovation, and you saw on the previous page, R&D definitely comes into play here. And there is innovation that is needed to reduce the battery costs, and I think also some elements of sustainability. As Bushveld, we're closer to the material, so we're not going to really focus a lot on innovating on the cell stack side or even on the battery design. But what we can do is work with the battery companies and think about things around electrolyte requirements. Can we offer electrolyte as a rental and really take away a massive piece of the CapEx, convert it into OpEx, and maybe even create a funding mechanism behind it? Electrolyte recycling. We know that it's fairly inexpensive compared to other batteries to extract the vanadium back, or to even repurpose the electrolyte into another battery. So all of these things are unique to the tech. What can we do as a supply chain participant? And other things that we've done is also maybe support some of the companies through investment, thus creating the stronger linkage. And then look, sometimes we get in trouble for doing all of these things. Even some of the battery companies themselves sometimes question whether we're doing too much. But our alternative is really to do nothing. And I'm always kind of proactive in saying if I can find a commercial case for it, I'm going to do more rather than do less. And then another step that we are doing is, and this is more confined to Africa where we're located, is, well, we're actually deploying the system. So we're kind of trying to drive adoption of the technology, put it with the utility that I've only had lithium ion, or installing mini grids at our own mines. So that's something that we're also doing. And then the last thing that I would just leave everybody with is there's an element of communication that has to happen. And certainly this is why, IFBF is so important for us. For those who participated yesterday at Vanitech, we had a session around, is there enough vanadium? What is needed? What is the market doing? And, some people say that, VRFBs or flow batteries needed an Elon Musk. And frankly, there's only one Elon Musk. And for better or for worse, that's the case. So the onus is really on us to communicate about the technology, about the use cases, and it's got to be every single participant, not just relying upon one company or one entity or one person in the case of flow batteries. So thank you very much for your attention, and Anthony, I'm going to turn it back to you.
Thank you very much, Mikhail. That's good. Rick Winters, President and CEO of UET. Rick's been at the forefront of electricity storage since 1990, leading the development of storage technology at PG&E in California and building microgrids in Australia's Torres Strait. He's led product development at 5 advanced battery companies and received the NatBat Lifetime Achievement Award and ESA's Phil Simmons Award in recognition of his outstanding contribution to the energy storage industry. He holds several patents for flow battery technology. Rick co-founded the ESA, served as its chairman on two occasions, and has been an enthusiastic supporter of the IFBF since its inception. He's fully occupied with the development of UET's Reflex product, the culmination of a $500 million investment in vanadium technology. And Henrik Buschmann is Vice President at Schmid Everflow. He's 11 years experience in battery technologies, including lithium and vanadium redox flow batteries. And under his guidance, Schmid Group identified the vanadium flow battery as a promising technology several years ago and developed working systems. Recently, Schmid has entered into joint venture arrangements for large-scale manufacturing. So we're going to hear first from Rick and then from Henrik and talk about how the industry will respond. So Rick, would you unmute your microphone and over to you, please?
Excellent. Thanks, Anthony. Really appreciate the opportunity. It's been some very interesting and exciting presentations given this morning. That's great. Also, the sun is now rising in San Francisco, and so another beautiful day coming along. So I promised you that I wouldn't talk too long, and I do a couple of 3 slides, and that a picture says 1,000 words. So therefore, there's already 3,000 words in these next slides. But I did want to give you a quick rundown of where we are, what we're doing, and then to be able to follow into the questions and answering questions session. So what you're looking at there, actually, right there in the middle there, is the culmination of quite a large investment in the vanadium space. It's the culmination of learning a lot, eating a lot of crow, figuring out which way to go, and how to deliver on the 50-year promise of flow batteries. So what you're in the middle there, that Reflex product, is actually a gigawatt-hour battery, right? And so we'll get to that. And it's really important to think about this. And I loved Matt's comment earlier on about thinking about throughput. So when we I've been working in flow batteries now for 25 years, and grid storage for 30 years. It's been an exciting ride from the microgrids in the Torres Strait to managing large utilities, PG&E's electricity storage program, and figuring out strengths and weaknesses and how to get to a technology that is really abuse tolerant enough and with high enough performance to be a utility asset. When we talk about chemistry, I think this is actually pretty exciting when you think about how to develop a product that's suitable for large scale deployment. And so it starts at the molecular level. So you need to go from molecules to megawatts to figure this out. And very briefly, to think about the molecular level of something as complicated as electrochemical system, and think about what's needed in the molecules. Right, and often as flow batteries, people think of flow batteries as these complicated things. It's not actually true at all. And we can see this when you look at the things that like lithium guys need to contend with. And we always think of a lithium battery relatively simple, this tiny little cell. Well, those guys have done a brilliant job in mitigating and compromising to deliver a product, right? They do a few, just to name a few. What are you managing? You're managing thermal runaway, flammable materials, recovery, downtime, degradation, side reactions, dendrites, swelling with charge, stress fractures, hotspots, current gradients, ion maldistribution. And with all that, you want large scale end product so that you don't need to put 2 million of them to build a 10 megawatt hour battery, right? So that makes it a relatively complex problem. Flow batteries solve all of those problems at the molecular level, and then all you got to do is connect a few pumps, tanks, and stacks, and you end up with a product. So the net result of that is that the ideal, optimum, biggest lithium battery you can build today is about 5 watt hours, right? That's what a cell is, 5 watt hours. And people have spent hundreds of billions of dollars to make it bigger. But how big is it? It's 5 watt hours, right? That product looking at right in the middle there, it's a modular system. It's 10,000 times bigger, right? 4 orders of magnitude. It's 40 kilowatt hours, right? And you can use that for the next 25 years. So if you think about complexity from the molecular level, flow batteries are crazy simple. And by the way, it has no thermal runaway. You can get a footprint of 600 megawatt hours per hectare, all those sorts of things like that. So what we've learned is how do you optimize, where do you go with this? And we've come to this modularity approach, this modular approach, this flexible product. And I love one of the quotes from Leonardo da Vinci, which is simplicity is the ultimate in sophistication, right? And so we have just had a maniacal focus on simplifying the product, and any component, any element, any material that goes into that battery better be super reliable and the best and the highest performing thing that it can be. So that's sort of from a chemistry perspective. Now you've all had a moment to look through these other points. There's a couple of things to highlight. Lowest cost. This pushes us very strongly towards this kind of 10 kilowatt, 40 kilowatt hour product. One of the reasons is, and it's a little counterintuitive, and this is from a guy that was the biggest most ardent supporter of containerized flow batteries in the world for about a decade. And then I had to eat a lot of crow and change my thinking on that. 90% of the costs, actually quite a bit over 90% of the costs of a flow battery are in the top 4 components, and none of those components are dependent on size. They're all dependent on volume, right? An example is the electrolyte, that you can't buy it cheaper because you put it in a small bottle or a big tank. It doesn't make any difference the size of the tank you're putting it into. It only makes a difference of what volume you're going to procure, right? And then you can fit through the 3 other elements, just so I'm not, the other elements there would be the Nafion membrane, the bipolar plate, and the felt. So between those 4, you're well over 90% of the cost of your product. None of them care whether you cut them big or cut them small, right? So the traditional thinking that you need to make 700,000 gallon electrolyte tanks to save money, well, the only thing you're working on there is reducing the cost something like 5% of the system. That doesn't make any sense, especially when it's a lower performing system as a result, and your reliability goes out the window. And you end up building a chemical plant in the field, which is the very definition of an unreliable, expensive system, right? Anyway, so one of the things I'd like to mention, because I just can't go through a sentence without saying this, is that we're now achieving 700,000 hours, sneaking up on 750,000 hours of over 99% availability with this product. So no leaks, no degradation, with systems deployed in the field for up to 2 years. And we're pretty excited about that. And that's fully a function of simplifying that product down to the essence and optimizing the components that go into it. It is the innovative use of common materials. There's no unobtainium in there. There's no dreamium in there. It's just metal and plastic and salt water, right? So you need to do that, and it takes a few decades to figure that out. That's what we're talking about, delivering on the 50-year promise of flow batteries. And it's not because the guys back then were dumb. They're brilliant people. We get to stand on the shoulders of giants, right? You leverage that knowledge, you move it on, you leverage new materials, a breakthrough from from Pacific Northwest National Labs funded by the DOE, some of the most amazing membrane materials coming in from Chemours, to be able to get a high performance product. In terms of going further with support, you're looking for those global partners to offer this excellent customer feedback, this direct connection to customer existing service capabilities. And frankly, what do they need? They need bankability. They need investment grade warranty. They need proven reliability, and that's where we go. And then on the planet, just a quick comment on that note. One, supply chain makes a big difference to large global companies. They take safety very seriously. They take sourcing very seriously, responsible sourcing of materials very seriously, because they're looking at a long time frame. They're looking at a 20, 30, 40-year time frame. And they know that taking a shortcut is going to come back and bite them if they can come back and bite them. And my last point, profitable recycling. Profitability makes recycling simple. You can recycle anything, but if it's going to cost you twice as much as what you get out of it, then you need a complicated contracting structure to force some guy who never heard of the product before in 20 years to recycle the system. And you can see that effect every day. If the price of lead goes up, everybody recycles lead. If the price of lead goes down, everybody parks the lead acid batteries until it goes up again, right? So, and that's just something quite simple to say, recycle like lead. So profitable recycling makes it simple and makes it happen. Next slide, please. So on this slide, I just wanted to give you a quick perspective on the arc of our company. We went from over a 50 megawatt hour journey that's deployed systems. So coming in, so from molecules to megawatts, where you figure out what's going on, massive breakthrough from Pacific Northwest National Labs in the vanadium chemistry to be able to improve the longevity, to reduce the footprint by half, or actually when we implement it by 4 or 5 times, and make it thermally tolerant anywhere on the planet. And that was sort of some Achilles heels. So that's really, really important. We spent tens of millions of dollars developing what we believe is what I firmly believe is the simplest containerized flow battery in the world. What you're looking at there is a 100 kilowatt, 500 kilowatt hour module in a 20-foot box that only needs to be serviced from the front. And that is critical to reducing footprint, right? Then we went out and we figured out and put it in the field. We put dozens of units in the field, and then we got slapped on the hand by the customers. The most important design contributors to your product are the customers. And that's when we figured out that the design spec for a flow battery must be, you need to be able to fit it under a door, and you need to be able to move it with a pallet jack, period. So we did a pivot to the Reflex product. That's exactly what you can do with it. Done the field validation work now, and we're into the market launch side. And then one of the things, so that's where we are as a company. And we have, as I mentioned, 720,000 hours of over 99% availability of these units with no capacity fade in the deployed systems. Next slide, please. So coming to volume, this is a little bit of fun. That's literally what a quarter gigawatt hour assembly line looks like there in the middle. It's pretty small, it's somewhere between 5,000 and 10,000 square feet. Basically, it's a Lego assembly facility. It's not 200,000 square foot production facility with toxic or flammable materials. And this is one of the, obviously you guys all know this is one of the tremendous benefits of the flow battery product is this innovative use of common materials that you plug together. You're squeezing plastic, you're dissolving salt into electrolyte. And that enables a really compact footprint. It enables pokey-okey design to make sure mistake-proof assembly. And it enables the really high volume of production. And that quarter gigawatt hour, by the way, is off a single shift for that line. So that's sort of where we've come from, where we're going, and where we are and where we're going. And with that, I'll hand it back over to you, Anthony.
Thank you very much, Rick. We'd like to just go to Henrik and to hear what Schmid are doing. Henrik, over to you, please. Please unmute your microphone.
Yes, can you hear me?
We can.
Okay, thank you, Anthony. And thank you, Rick, for that enthusiastic speech about flow batteries and giving insights into all your development steps. So yeah, we at Schmid, so let me introduce myself first, Henrik Buschmann. So I'm the head of the battery activities here within Schmid, or as we now will be named Everflow, like our product has already been named in the future. So we're in business with the flow battery since 10 years. We have spent a lot of time in developing different kinds of systems, mostly containerized units. And after reaching a certain level of maturity, having field experience, etc. So we also had to look into how will we manage to be compatible on the market. And at that time, we had to realize that we had to go big scale in order to be compatible with other technologies, etc. So we were then looking, for suitable partners. And as Anthony already said, we could now close the joint venture together with our partner from Saudi, SABIC. So SABIC is a company coming from the petrochemical industry, so they are very well experienced in, of course, plastic materials. And Schmid is coming from the equipment manufacturing side, so we have more than 150 years of company history experience in equipment manufacturing. And so these combined company skills will for sure be a big step for us in the next coming years to be able to produce batteries in large scale. And also we see the local market in Saudi as very important. Yeah, this is a brief introduction of what we do. And yeah, let's carry on.
Henrik, thank you very much. I mean, I think it's fascinating that you've chosen the step to build your manufacturing plants in Saudi Arabia. It gives you great confidence. I think probably just having heard those replies from three people in the industry, I'd like to go straight back to Kenneth and ask him the question. Kenneth, do you think it's credible that these flow battery manufacturers can gear up to provide the supplies of flow batteries that you've seen the demand for in the United States and elsewhere? Kenneth.
I certainly hope so. When I look at kind of the scales here, I think more to kind of a load-based application first. The large generator applications, they're already in the hundreds of megawatt hours. The data centers are kind of still more dipping their toe in, kind of on behind the meter, and that's probably the time to get on the train, and use that to kind of scale up. And it was actually some things, that Mikhail said, gives me confidence kind of on the financing. Even if the electrolyte cost is significant, the ability to lease or rent that, I think it's from my point of view, it's a great idea and will really bring down the barriers to adoption for this sort of technology by data center customers.
Thank you very much. Henrik, going back from the point that Kenneth raised about bankability, you've been fortunate in getting the finance and a joint venture partner to build your new factory for Everflow. What can you tell us about bankability of your future product when, to be honest, you haven't even started really building it at scale? So how do you think customers will be able to get the finance to secure any projects based on your technology?
Well, yes, we haven't started the production in Saudi yet, this is true. But as I have mentioned before, we have experience in building systems. We have systems existing in the field. So this is experience we can build on. And yeah, for sure, we will have to go through evaluations. But, with also a strong partner in the back, we think we can tackle these.
Thank you very much. Mikhail, do you have anything to comment on the manufacturing aspirations of Rick and Henrik?
Well, I hope they're really successful, and I'm gonna, well, not I'm gonna, I already have reached out and said, where are you gonna get your vanadium from, and where are you gonna get your electrolyte from? So I think, from our point of view is, we want the industry to be successful, and we want to create more demand into energy storage from vanadium, which at the moment primarily goes into steel. And our goal, we've stated publicly, we're trying to triple our production output. Where's that vanadium going to go? I would be so happy, and our board would be so happy if a lot of that went into storage. That may not be the mindset of every single miner or every single vanadium producer, but that's what we're trying to do. And really my entire focus is, how do I make that happen? And look, if it's other producers also supplying, that's absolutely fine. It's a commodity, so it ends up being a closed market. We just need to make sure that there's enough supply to meet that demand, and then we need to make sure that the battery companies can be successful to meet that, to actually create the demand, and then that's where scale of manufacturing definitely comes in.
Thank you very much. Adam, I hope you're there. Can you hear us, Adam? Okay. In which case, can I come back to
I was going to say, Adam, I think, is found himself traveling. It's an unfortunate place where he doesn't have reception, so I can try to answer.
In which case, Kenneth, thank you very much. Kenneth, question for you about national policy. Do you think it's credible that huge resources required to boost a nation's energy infrastructure would be reliant on materials, equipment, and items that were sourced from outside their own national borders?
Obviously, the answer has changed a lot in the last 6 months, and I think it all comes down to it depends. I think the nice thing about, let's say the vanadium is, when you order it, you can get it relatively quickly. So if someone's putting in a VRB system, you don't need to continue to use procure more vanadium. You have it once, and then if there's a supply chain disruption, your battery still works, which is going to be different from things like pharmaceutical precursors and other things, which have become at least a hot topic here in the United States post-COVID. So I don't think it's as much as a worry as anything else, because it's a one-time order, more of a capex than an opex.
Thank you very much. Andy, can we go over to you, please, and pick some questions for us from the floor?
Sure, yeah. So we've there's a good one that's come up a few times following Kenneth's talk, but I think it's relevant to everyone, which is how do they see long duration batteries like flow batteries being positioned against things like hydrogen or biodiesel, for really long applications in microgrids or where people are looking to be 100% renewable?
So I don't think biodiesel is going to kind of check the box for a lot of the data center companies. I think there's unfortunately still a lot of greenwashing going along with that, and it's not scaling. Hydrogen, to be perfectly honest, I've looked at it so many times, I cannot, and I still can't understand the hype. The implied cost of energy out of hydrogen because of the CapEx is still unfathomably high. I do think it's gonna pass by. I mean, 15 years ago, when I was working at the National Renewable Energy Lab, that was the last time that the United States had was all excited about hydrogen, and then it waned. And I think this too shall pass. I could be wrong, but if I was a betting man, I'd certainly bet on the technology we're talking about here over hydrogen.
Thank you. Andy?
Yeah, great. So another one that's maybe well suited to Mikhail is about electrolyte rental and what the benefits are. I guess they're looking in terms of other than simply reducing the capex up front.
Well, yeah, I mean, so that there's financial, I like to think of it as financial benefits and non-financial benefits. So the financial benefits is, yeah, you've got an element of taking capex, turning it into opex. But the other thing is you don't need to recover 100% of the capex because you know that there's a residual value. So you can actually factor that into your upfront kind of financial model. The third part is also the fact that you can get financing for this or at a lower cost than just, let's say, your typical project financing. Because in addition to that rental stream, which is basically the creditworthiness of your off-taker, which you would have in project finance, you've got an additional collateral that is a lot more easy to redeploy, which is vanadium. So it's a less risky asset. And then there's another reason why it might be cheaper, which gets into the non-financial benefit, which is the sustainability. So today, if you have a rental structure, you've actually de-risked what is going to happen with this material in 10 years, in 20 years. So that chemical itself, which is really maybe the most difficult piece to solve for, rather than the plastic or the metal that goes into the battery, you already are saying, no, I've got a solution today. Yes, there's a financial solution on it, but it's still got a technical solution where I know where I'm going to go and reprocess it, and I know what the cost is, and I've already funded that. So that means from a sustainability point of view, I've got a much better and cleaner situation than I do with lithium, where I'm hoping all of the minerals will be, recyclable by the time that this battery, ends. Maybe the cobalt is already worthwhile, but I don't know. Here, not only do I know, I've already got a financial product on top of it that justifies the fact that I'm going to do this. So I think that just makes it a whole lot more attractive with anybody who's solving for not only financing or costs, but also for sustainability.
Thank you.
And I want to add in there, I really want to highlight what Mikhail is saying about the financeability. When we go to our tax equity and project finance investors, and present to them, let's say a Tesla battery. Their concern is, hey, there's a Tesla warranty, but one tweet from Elon Musk, and all of a sudden that warranty can become worthless. So what's happening in the U.S. right now, I think, is actually the wrong trend because of the upfront investment tax credit. The battery manufacturers are increasing their upfront capex because you get a third back from Uncle Sam. And in doing so are offering longer extended warranties, because then you get a third of your warranty paid for by the federal government. That is, what I hope to be a temporary phenomenon when the U.S. investment tax credit starts rolling off, as it is right now. I think you're going to see a swing back to more of an OPEX heavy model, where, as Mikhail said, you can get better financing. We don't have to worry about the risk. Mikhail, you're much better to finance it because you know how to repo, vanadium. HSBC does not. You can underwrite the long-term value. And I'll point to, this is already happening today in the renewable markets, especially for solar, for land. Today in the United States, when you finance a solar project, you will have one owner owns the land and they will lease that to you long term, and then you finance the equipment separately because it's more efficient to start breaking the parts of the project and having the individual investor who will give you the best cost of money, and can take the longest term view on each of those aspects. So, Mikhail, I absolutely applaud the direction you guys are going. Okay, thank you. Can I just come back to both Henrik and Mikhail? We've heard much about the position in the United States and North America, but we have in Europe a totally different structure of our energy industry. It's different in much of Asia, and of course it's different certainly in sub-Saharan Africa. So first of all, Henrik, any brief comments on the way that the energy industry is structured in Europe and how this might affect large-scale purchasing of storage? Henrik.
Please unmute yourself.
Henrik, you need to unmute yourself.
I'm sorry, I dropped out of the Teams meeting completely in between, so, so now I'm back. So the question is on the market in Europe. So yeah, I think what we've seen in Europe so far from utilities is not so much the demand for long duration storage. It is expected to come, but it's maybe not so let's say obvious, also close like in other regions on planet Earth, right? So so therefore we are currently not so focused on Europe actually, but more to the other countries that have more demand for long duration storage.
That's interesting. Mikhail, what's your view from sub-Saharan Africa, please?
Yeah, well, so it's a lot of different countries, and they all have different requirements. So I think one application that is especially prevalent, well, two that are kind of unique to Africa is the mini grid or microgrid use case. Not only just kind of individual villages and households, but there are already grids that are powered by diesel or heavy fuel oil that are trying to decarbonize and reduce their costs by adding solar. So our big push is, well, just leapfrog that, add immediately solar long duration storage, and go from a carbon-based grid that has 10 or 20 megawatts of load to and if you add solar, you're going to 20-25% clean energy. You add long duration storage, you're going to 70-80%, depending upon what the seasonality of the solar is. So that's one. The second is, outside of South Africa, and unfortunately increasingly in South Africa, the grids where they do exist are unreliable. So there's a use case that is very good to a flow battery where maybe you're expecting to run the battery multiple times per day. Once with that, with your kind of self-generation from your solar behind the meter, but maybe another time you might be charging it when the grid is available, and you might actually increase your load from the grid at that time. So there could be a cost arbitrage. Because usually grid, when it is available, is actually quite a bit cheaper. So there could be some unique cases from that. And then, we are slowly getting a lot more independent power producers that are either wind or solar. And there are increasingly questions around dispatchability of that variable energy. And, whereas the first tenders did not include that requirement, increasingly there are requests from government, I think to some degree supported by the World Bank and some of the DFIs, to add dispatchability to that. And the criteria could be extremely long. They could be for 4 hours, but they could actually be in South Africa. They're thinking from 5 a.m. until 9 p.m. If you're building a new solar plant, you've got to be dispatchable energy for that whole duration. And how do you solve that without long duration storage? You can't, unless you've got multiple generation technologies you can put in there.
Mikhail, thank you very much. It's been an absolutely fascinating afternoon. We've heard lots about data centers. We've brought in the whole realm of renewables. We've talked about dispatchable energy. We've talked about microgrids. Much of this has been made possible by Adam's foresight in putting this panel together. Adam, I think you just managed to come back to us. Have you got any comments that you would like to add? If you need to unmute your microphone, you need to use *6.
Thanks, Anthony. and thanks everybody for joining today. Sorry for the technical challenges, and I'm sure you can appreciate Ken's perspective. I just was listening now to Mikhail. A couple of things that we pay a bit of attention to here, and that is everyone is looking at the notion of a temporal shift of power. That's what batteries do. I'd like to suggest that we begin considering the physical shifting of power, right? So we can arbitrage time, but we can also arbitrage space. But even when you put that on the table and you say, all right, I get it, maybe we can transport batteries or electrolyte or both analyte and catholyte, perhaps we as an organization can ask even a deeper question. And it might sound like this. Under which circumstances would a flow battery be the only asset indicated for a particular purpose? And that the answers to those questions, there are real answers to those questions, and they are not universal. And that basically creates a difficult challenge because centralizing and deploying assets is usually efficient when we have a community to deliver to, whether that's a state, a nation state, a province. But what if our society is changing right in front of our eyes? We already know that people are leaving, and I'm not in South Africa by way of example, but here in America, people are leaving the cities at such a rate that the rural properties are selling at, it is absolutely shocking, perhaps alarming. The load is shifting. We have foreign nation states that are thoughtful about our infrastructure here in this country, and other countries have been at war. Today, weapons to create EMP devices, right? EMP devices can decimate major cities and populations. What type of assets could function in the universe where we absolutely had to have power and efficiency wasn't an issue? I want us to be thinking, if Anthony, you've asked me a question, what I suggest, we should be looking in the next 60 years and asking, how can a flow battery deliver power to people who need it? And how will nation states think differently about ultra long term? And where is the vanadium coming from? I think the whole world is going to be depending on Mikhail much more than they're paying attention to today. I think his company is in the center of this entire industry, and we need his leadership, and we need his assets, and I can't make it any simpler than that. So I'm sorry I was late today. My friend Ken Davies, you've met. I have to tell you, Ken is one of the leaders in the world in this renewable energy space, and I'm grateful he spent some time with us today. So thank you, Anthony. Thank you, Mikhail, and that's all I have.
Adam, thank you very much indeed for your contribution, and we appreciated that. Just before we close, can I just go back through our speakers for this afternoon and ask if they have one last final comment? Sorry, that's a tautology, isn't it? They have a final comment from themselves. Henrik.
Yeah, I think we've heard a lot about the cost issue today, and I was just thinking, why is it not possible to have a structure that gives more confidence for the customers, that some vanadium producer could say, okay, whatever type of electrolyte you can bring back, so we will definitely purchase it for a certain price, let's say spot market minus something. So I think this could create a lot of confidence.
Thank you very much. Rick.
There we go. So thanks, Anthony. I think one of the areas that is most compelling we're looking forward is to focus on increasing duty cycle. So people often talk about capex costs or total cost of ownership in the absence of value, of the value stream. One of the things that the flow batteries can do better than any other battery is provide a higher value stream. And what I mean by that is a really good example. If you had, for example, a battery that cost you $500 a kilowatt hour and it lasts 25 years and you use it 100% duty cycle, that drops it to 2.2 cents per kilowatt hour. We talk about vanadium being expensive. If you do the same thing with vanadium, that drops it to 0.3 cents a kilowatt hour for the raw materials, right? So I think it's super important that we focus on expanding the use cases and getting that duty cycle up. The ideal is 100%. And that does a couple of things. Obviously drops the impact of that CapEx. Well, obviously we want to need to drive the CapEx down too, and we're toe to toe with lithium on the reduction rate. So and except we're at the beginning of the curve and they're towards the end. So I think there's great opportunity there. But I think so that's the focus, is to look for applications and look and teach customers and learn with customers on how to get more and more use out of the battery. Because remember, the more you use a flow battery, the cheaper it is. The more you use a lithium battery, the shorter it lives. So it's a really fundamental difference there. And it's a topic that the lithium lads are not going to touch. They don't want to get people to use the battery more and more. That's the area that the flow battery industry needs to push, higher value from a product.
Super. Thank you, Rick. Mikhail.
Yeah, so I would agree with that. You know, the use cases, you know, right now it's about deployment. We know the tech works. There's batteries that have been operational for years, different sizes. There's a lot of companies. It's a mature sector. There's investment funding going into it. So it's just really about deployment. I think that, you know, also hearing from the different panelists, to some degree, the technology is so captivating. I think we're actually maybe scratching the surface of where it could be used. You know, I like batteries more than other types of storage because of the flexibility, but some of the other things, you know, that I saw here that are actually making me think, oh my gosh, you know, the flow can actually be used a lot more. But yeah, let's, you know, I think we're at a point in the sector where it's around deployments and getting systems into the market. Which then will lead to innovation on the supply chain and probably also even more innovation on the use cases. And Anthony, I think what I like about where some of the presentations in the IFBF have been today is actually thinking about, you know, where are these things being deployed, or at least where could they be deployed, which is really the good direction. There's always an important part which is technical, but in the end, if something is not deployable and there's nowhere to use it, you know, it's just becomes a theoretical exercise, whereas, you know, we want to make this a practical and commercial exercise.
Thank you very much. Kenneth, your contribution's been great. It's so pleasing to have a potential customer along to an IFBF demanding for us almost to produce products to give you to get into the marketplace. So we're going to straight away say to you, you know, do come back next year and tell us what you've bought and how you've deployed it. But do please, have you got any comments on what you've heard from the rest of the panel?
Yeah, I think I'll just end with highlighting the fact that think about data centers and, you know, their potential willingness to pay more than a market price. What do I mean by that? You know, when I was at Microsoft, we consistently entered into renewable energy transactions where we expected to lose a lot of money. You know, I took a specific deal forward I'm thinking of and told Microsoft management we were going to lose $250 million. And it took 15 minutes to get it approved because of the story. So help us tell the story. I would joke when I was at Microsoft, I had the world's largest marketing budget. These data centers are in the market, hungry for differentiation. Another renewable deal just doesn't move the needle. Help the data centers move the needle, tell the story, and they will pay a premium well above and beyond what you would ordinarily think.
Thank you very much. Adam, I think you've, you're not there, but thank you very much indeed for hosting this session and pulling it all together and giving us the inspiration for this. Your story and vision have been incredibly useful. So that really concludes today's session. We hope you found this informative and useful.